Okay, dear students, today I am going to derive the expression for fringe width in Young's double slit experiment. So in the last class, previous session, I have discussed the Young's double slit experiment, also Young's experiment in the original version. The fringe pattern is as shown here. Central of the fringe, we take a central bright fringe. I have shown here as O. Center of the central bright fringe. The intensity distribution curve will be like this. So center of the central bright fringe. So we can take a distance along the x-axis and intensity along y-axis. So the center of the central bright fringe, the intensity is maximum, and then intensity decreases. So this is the first dark fringe. This is the first dark fringe, and this is the center O, first dark fringe. Then and this is the second, first bright fringe. This is the first bright, and this is the first dark here. And this is the maximum intensity is same for all the fringes. All the fringes have equal intensity. So this is the here like this it comes. So the intensity is maximum and same for all the bright fringes. You can see this bright fringe, first bright fringe, second bright fringe, third bright fringe on either side of the central maximum here. You can see all the bright fringes have equal width as well as same intensity. So now fringe width means distance between the successive bright fringes or successive dark fringes. So that distance is called as fringe width. Now you see here, center of the central bright fringe. This is the central bright fringe. O is labeled central bright fringe. Okay, central bright fringe. Now first bright here. This is the first bright. So this distance on the screen is called as fringe width. Distance between the successive bright fringes is called as fringe width. Similarly, distance between the successive dark fringes. See, third dark fringe is here, middle between two bright fringes, second bright and third bright. There is a dark fringe, third dark fringe, and here fourth dark fringe. Now, distance between the successive dark fringes is also fringe width. So, fringe width is the distance between two successive bright fringes or distance between two successive dark fringes. So that is distance. That distance is called as fringe width. And the expression for fringe width is lambda d by d. Beta equal to lambda d by d. Okay, so this is the fringe width expression where lambda is wavelength of the light, and d is the distance of the screen from the plane of slits, and small d is the separation between the slits. That's all about the idea. So now you see this diagram once again I will tell you. This is the intensity distribution curve in interference. Intensity along the y-axis. Okay, intensity along y-axis, and x-axis you can take distance, or you can in the textbook they give path difference. If you take path difference, then what you have to take here is this is lambda by 2. And this is lambda. If the path frequency is lambda, then the value of intensity will be 4I0, maximum intensity. Okay, for lambda. If it is 3 lambda by 2, then dark fringe intensity is almost 0. Here lambda by 2, this is lambda on both the sides. Okay, so minus lambda by 2 you can take minus lambda minus 3 lambda by 2. For such path differences we get dark. Minus lambda by 2, minus 3 lambda by 2, lambda by 2, 3 lambda by 2, 5 lambda by 2, etc. We get almost 0 intensity when you take two sources, two slits illuminated with the same intensity. Two slits, each slit giving out light of intensity I0. Dark fringe will have intensity 0. You can see here dark fringe means absence of light. And bright fringe means not necessarily white. The fringe may be red in color. All bright fringes will be red. If you use yellow monochromatic light, then all the fringes will be yellow, and in between there will be dark fringes. So that's the idea. Now I am going to do the derivation of fringe width. Okay, this is the fringe pattern. Okay, derivation of the fringe width. So I said definition of fringe width is distance between two successive bright fringes or two successive dark fringes is called as fringe width. Now this expression I have to derive. Okay, for this there is a diagram. Okay, so diagram is like this. So here we take the plane of slits like this, and we take the screen here. Okay, so this is the plane of slits. Okay, this is the slit S1 and this is slit S2. This is the plane of slits. Plane of slits. And this is the screen. And here light of wavelength lambda illuminated on the single slit first, then on the two slits. Now at any point here, middle of the screen, we take this point as middle of the screen O. Okay, at any point P here, maybe a bright fringe is formed. I assume at point P there is a bright fringe formed, nth bright fringe. So I will take this point to here distance, okay, like this, and now we will draw the opposite, so like this. So the experimental setup you see, it is discussed in the previous class, only part of that experimental setup. So distance between the two slits. So two slits are illuminated by the single slit, light from single slit falls on the two slits, each will give the intensity of say I0. The slits are very near actually and very narrow. Distance between the slits be small d. This distance be small d, and distance of the screen from the plane of slits is capital D. And midpoint is O here, and this distance will be d by 2. Okay, this distance, and even another power half also d by 2. Now the distance of the point P from the center of the screen. Okay, center of the screen or center of the fringe pattern. So that is x. Okay, so this distance equal to x. Distance of the point P where I assume there is a bright fringe. It can be dark fringe also. Then next, the point O to P distance is x. Then what happens, you see, this distance. Okay, I will take opposite to S1 as point E and opposite to S2 this point as F. Now this distance, you see, this distance, two distances are there to be labeled. Okay, one is this EP. So this becomes x minus d by 2. Distance P, distance of the point P from O is x. Distance of the point P from E, this EP is x minus d by 2. Total is x, in that d by 2 have to reduce. So it becomes x minus d by 2. Same way, another distance FP is x plus d by 2. So this becomes x plus d by 2. X plus d by 2. So this is the distance. So then after that, now the diagram is completed. So light of wavelength lambda is incident on the two slits. Light of wavelength lambda is incident on the two slits. So that is the wavelength. Okay. Now in the figure we can see S1P, S1EP is a right angle triangle. S1EP is a right angle triangle. So applying Pythagoras theorem. Okay, Pythagoras theorem to the triangle S1EP. So what happens? S1P square is S1E square plus EP square. Okay, substituting the values. S1P square is S1E square plus EP square. So that is equal to d square plus S1E is d, distance of the screen from the slits. EP square, EP is x minus d by 2. That square. Okay, so that is S1P square. Similarly, what we can write in triangle S2FP. In triangle S2FP, we can write S2P square. S2 here, this point P square. This square of the hypotenuse is equal to S2F square plus FP square. S2F square is how much? D square. So d square plus fp square. Fp square is how much? X plus d by 2. X plus d by 2 square. So this square is d square. Fp square is x plus d by 2 square. So that I have to add square. Now this is equation 1. This is equation 2. Now to get the path difference I have to subtract. So 2 minus 1 gives 2 minus equation 2 minus 1 gives, see, s2p square minus s1p square, s1p square equal to, see, subtracting first equation from second equation, that is 2 minus 1. So this minus this, s2p square minus s1p square LHS, d square minus d square cancel, d plus x plus d by 2, x plus d by 2 square minus this terms. So subtracting this corresponding term we are subtracting. X minus, here minus is there, minus d by 2 the square. Okay, so this is the thing what I have here. Okay, so this is the difference. Now we have to simplify this part. So s2p square, LHS same, so simplification. Now can we expand this? A plus b whole square formula we can use. So x square plus d square by 4 plus 2x into d by 2. Okay, then minus of x square plus d square by 4. How? It is a minus b whole square. A minus b whole square is a square plus b square minus 2ab. So minus 2ab. A is x, b is d by 2. Okay, so this. Now you see what happens. You see x square minus x square cancels. Here outside minus is there, and d square by 4 and this d square by 4 cancels. Then 2 and this 2 cancels, and this 2 and this 2 cancels. Carefully observe. This 2 cancel. X d remains here minus, and one more minus inside. So minus of minus plus x d minus of minus is plus x d. So xd here one is there, and minus of minus is plus xd. So this is 2xd. LHS is 2xd. So this is a square minus b square form. LHS also. That is a square minus b square is a plus b into a minus b. So I use the factorization. S2p minus s1p into s2p plus s1p. So that is equal to 2xd. Okay, so you are getting s2p, a square minus b square means a minus b into a plus b. So s2p minus s1p into s2p plus s. Now what I do, I take only LHS s2p minus s1p equal to, I take this sum term is not to the RHS. So 2xd upon, okay, denominator is s2p plus s1p. The second bracket, the second factor product I am shifting into RHS. So equation number 3. This equation I will take it as 3. Okay. Now condition for path reference is there, and also see this S2p plus S1p. So that distance adding, so S2p and S1p as the point P is very near to O only we take. It is not far distance. So with one approximation, when the point P is close to O, and also D is very small compared to capital D. The distance small d is very small compared to capital D. Then what happens, you see, the distance S2p plus, okay, nearly S2p, S1p, nearly equal to capital D. Then for the denominator part, S2p plus S1p is there. So that one I take plus S1p nearly, and I add this also nearly equal to capital D. This actually the distance is very small, small d is very small, and the point P is also very near to O. Then I can say S2p plus S1p is 2d. So that is the denominator. So then what happens, you see, equation 3 becomes how much? S2p minus S1p. S2p minus S1p is difference? See, light going from the slit S1 and light is also going from the slit S2. Light is going from two slits. Okay. So the path, extra path traversed by the second slit. Light going from slit S2 is traveling extra distance. How? If I put a line like this, you see. If I bring the point S1 here and then this path is the extra. If I bring the point S1 to this somewhere coinciding with the line S2P, then point S1 comes to this point. So this is the extra path that has to be traveled by the light going from slit S2 when compared with the light going from slit S1. So that is the point. So extra path, that extra path means path difference. Path difference between the light traveling from the two slits is this, that is xd by d. Okay. So that equation number 4 I will take. This is the path difference. LHS is there, this term is the path difference. This is the path difference. Okay, this term is there. This is the path difference between the light traveling from the two slits. Okay, so now what you have to do? That path difference. If path difference equal to S2P minus S1P equal to n lambda, then I get a bright fringe at P. Okay, we get bright fringe if the path difference equal to lambda. That means this distance S2 to S1, this point. Instead of S1 I write some point n. Okay, so then S2n, if it is lambda or 2 lambda or 3 lambda, etc. If it is 1 lambda, full lambda, or 2 lambdas, 2 waves, 3 waves complete, then that point P will be the bright fringe. Bright fringe is formed at the point P. Okay, so that bright fringe will get. So then what happens? Compare the two equations, that's it. That is xd by capital D equal to n lambda. xd divided by capital D. Small d is distance between the slits, capital D is distance of the screen from the slits. So xd by d RHS, LHS is path difference, and path difference condition we have seen in the previous class after the theory of interference. That path difference equal to n lambda, then we get a bright fringe. So comparing this from equation 4 and equation 5. Okay, so from 4 and 5, what we can write? xd by d equal to n lambda. xd by d equal to n lambda. So that implies x equal to take d, that's it, n lambda capital D divided by small d. This is what x I get. X means I said distance of the point P from the center of the fringe pattern or center of the screen. Now generally we say nth bright fringe. This is x. X is any bright fringe, I don't know. I say nth bright fringe. X is xn I will take. So if I take, okay, so here I will take xn. Instead of x I will take xn. Distance of the nth bright fringe. Here nth bright fringe is formed. And next bright fringe will be n plus 1th bright fringe. Okay, and that distance from O is xn plus 1. So xn, what I can write? N lambda d by d. And also same way xn plus 1, n plus 1 bright fringe. Okay, so what we have to do here? In place of n, put n plus 1. So then it becomes n plus 1 lambda d by d. N plus 1 lambda d by d. Correct? Xn, distance of nth bright fringe from the central maximum or center of the fringe pattern or midpoint of the screen. Okay, so that is xn. Xn plus 1 is distance of n plus 1th bright fringe. Now what is the fringe width definition? Distance between the two successive bright fringes is the fringe width. Distance between the two successive fringes is the fringe width. Successive bright fringes. Okay, so here successive bright fringes. So this is the slits, this is the screen here. Okay, don't forget this is the screen. It is not a line, it is a surface, plane surface. Now we have to subtract, that's it. So what I have to get? Beta equal to xn plus 1 minus xn. What I have is xn, n lambda d by d. Xn plus 1 is n plus 1 lambda d by d. Substituting here, I get the fringe width. See what happens? N plus 1 lambda d by d, okay, minus n lambda d by d. Okay, n plus 1 lambda d by d minus n lambda d by d. So lambda d by d is common. So then what remains outside? N plus 1 first term common minus n into lambda d by d. Okay, so I write at the top here that I will repeat. So fringe width beta equal to xn plus 1 minus xn. Xn plus 1 is n plus 1 lambda d by d, that's what we got. Xn plus 1 symbol means distance of n plus 1 bright fringe from the center of the screen minus xn, distance of n bright fringe, n lambda d by d. Okay, so then lambda d by d is common. Lambda d by d is common here also, here also. What remains in the first term? N plus 1. What remains in the second term? Minus n. Okay, so n and this n cancels after subtraction. So what happens next? This much only remains. It is 1 here. So therefore beta equal to lambda into d by d. So this is the expression for the fringe width. So what conclusions we can draw from this expression? Fringe width is directly proportional to wavelength. Means if you use a longer wavelength light, like red light is having longer wavelength, or orange light, yellow light, fringes will be broader. And if you use violet light, indigo, fringes will be narrow, okay, because wavelength is less. So longer wavelength, when you compare two wavelengths, whichever is longer for the given experimental setup, means keeping capital D, small d same, only changing lambda. Longer wavelength, red is giving broader fringes compared to orange. Orange giving broader fringes compared to yellow. Yellow giving broader fringes compared to blue. So like that, we have to go Vibgyor order. Vibgyor means wavelength increasing order. Least wavelength violet, longest wavelength red. Violet, indigo, blue, green, yellow, orange, red. This is the way wavelength increases from violet to red. Now it also depends on capital D. Okay, that means if the distance of the screen is increased, fringe width increases. So what does it mean? If you move the screen away from the plane of slits, if you take the screen away, fringes become broader. That means increasing capital D directly proportional to beta. So therefore increasing D, fringe width beta increases. Increasing lambda, fringe width beta increases. And lastly, what about D, small d effect? Decreasing D, fringe width beta increases. This is inversely. Beta inversely proportional to D, means if you bring the slits near and near, then fringes become broader. Okay, so that's the idea how fringe width depends on these numbers, these variables. Okay, wavelength directly means longer wavelength used, then fringe width increases. Capital D directly, so if you increase the capital D, fringe width increases. If you decrease the small d, fringe width increases. So inversely proportional. So that is what the linear fringe width. Then I have one more idea, angular fringe width. Angular fringe width I write angular fringe width. Angular fringe width is theta. N bright fringe we can write it theta n also. Okay, theta that is equal to lambda by d. Okay, angular fringe width is lambda only, that is independent of capital D. Okay, so it is lambda by d is called as angular fringe width. That's it. Okay, that means it is also depends upon it depends on lambda and only small d. It does not depend on capital D. Angular fringe width. First bright fringe, second bright. If you increase the value of capital D, angular fringe width does not change, whereas the linear fringe width will increase. If you increase capital D, it increases. So what about the fringe pattern in case of red light, colored white light is used? We get colored fringes with the central white fringe, then violet near the this one then yellow fringe, like that we get different fringes. Okay, so that is for a white light. Okay, so this how it varies. This is important. Here question can be like this. What happens to the fringe width in Young's double slit experiment if yellow light replaces green light? Okay, so yellow light replaces green light. I have written the order here, wavelength order. So if yellow replaces green means what happens? We are using the longer wavelength, yellow. Later we are using yellow. Initially they are using, or we used green. Yellow replaces green means yellow came into situation or in the experimental setup instead of green light. That means we change green to yellow. That means we are changing the light from green to yellow. Fringe width increases. If you use this one, beta value increases. Okay, if you reverse it, if yellow light replaced by green light, see the wordings. So here in this case beta, yellow light replaces green light, beta increases. Okay, now the same this one words, small change I make here. Yellow replaced by green. Yellow replaced by green. Yellow replaced by green means what happens? Just see. Yellow light replaced by green light means yellow light is replaced by green light. So initially yellow light is used. Now we are changing into green light. Yellow light made into green light. So yellow to green means reverse. So in that case wavelength decreases. Green is having shorter wavelength compared to yellow light. So when wavelength decreases, fringe width beta decreases as the wavelength decreases. Green is having shorter wavelength compared to yellow light, therefore fringe width decreases. So this is how the wavelength affects the fringe width. And also same way capital D I said, if you take the screen away, fringe width will increase, means the fringes become broader. Distance between the bright and next bright will increase. And if you push the screen towards the slits, beta fringe width decreases. And if you take the slits near and near, then fringes become broader. If you take the slits near, fringes become broader. That is inversely proportional. So the graph between fringe width and capital D is a straight line. Graph between beta and lambda is also a straight line. Graph between beta and small d is hyperbola. This graph you must know this situation. The graph between beta and d. Beta here, small d here. This is a hyperbola. This is not a straight line, it is a rectangular hyperbola. Inversely proportional is the such situation, the graph will be rectangular hyperbola. That is y inversely proportional to x, that graph is rectangular hyperbola. So beta and d gives you rectangular hyperbola graph. So that's all about this today's class, that is the derivation of the fringe width and how the fringe width got affected with the various physical quantities used in the Young's double slit experiment. So that's all. Today I will stop the session.